projects. And so leveraging these HALs elsewhere, creates a greater maturity, right? They have been exercised in different contexts, and so we're not starting over from scratch. And finally, some of these, RTOSs, or excuse me, vendor HALs, at least from NXP, actually go through QA testing before we release them. So we have some known sense of their quality before they actually go external. And so the ultimate goal here is to simplify the process of adding new SoCs to Zephyr and adding new drivers to Zephyr that support those SoCs. So naturally, there are some trade-offs. We'd be kidding ourselves if we said, everything would be perfect by using these HALs. So, what are some of these trade-offs? So in the previous slide, I said, the code is maintained elsewhere, and there are some benefits to that, but there are also some trade-offs to that. I think the most obvious one is, if we find an issue, if we find a bug, it's a bit more difficult to upstream and fix that bug. Like I said, generally the licenses are compatible with Zephyr, but not always. We have seen cases where a vendor HAL it had a license that was new to Zephyr. So we've become accustomed to use Apache. We've become accustomed to use the BSD3 clause. But what happens when another license type comes in? We had one, I think that was a zlib or some other type of license. So we had to figure out how are we gonna, how could we make sure that that license was compatible, and how could, make sure that, we didn't encounter any kind of IP problems by incorporating that into the tree. And likewise, when the code is used elsewhere, sometimes those APIs are a bit more tuned to what those other ecosystems might be. So they might not always be compatible. We might have some issues where it doesn't quite fit together. It could also be that there are some features that we need in terms of what the Zephyr interfaces require, but maybe aren't implemented at that lower level HAL. So we have to look at those on a case-by-case basis and do what makes sense. We already have quite a few different HALs already in use in the tree. NXP is certainly not the only one. This is a list of everything we're using today. Starting up, I've got these in alphabetical order, so starting from ARM, we have the Synthesis HAL, which I'll talk a little bit more about next, that are used by pretty much all of the ARM vendors and build upon Synthesis. We have Atmel's Atmel software framework used in the SAM SoCs. Intel's using their QMSI, which is the Quark Microcontroller Software Interface. I hope I got that acronym right. Nordic has their MDK. We have our MCU Expresso SDK. In the previous talk, you heard Erwan talk about the STM Cube and how we're using that in Zephyr. And finally, we do also have an SDK from TI for their SimpleLink devices. So there are kind of three levels of abstraction of how we can use those HALs. So starting kind of from the most abstract sense, taking the transactional HAL level drivers provided by the SoC vendors. And so this is, if the APIs are compatible, probably the simplest way to get a new driver supported in Zephyr, because most of the heavy lifting is done in the HAL driver itself. And then within Zephyr, we have very thin shim level drivers. This is the approach that we've taken in the MCUX, which is the Kinetis and LPC devices from NXP, as well as the Intel QMSI drivers. So those are kind of, we've seen different vendors taking different approaches in terms of the levels of abstraction. So the highest level, the transactional level, we see in two of these types of devices. And then moving on to a slightly lower level of abstraction, we see a low-level kind of stateless HAL type of driver, which Erwan talked about in a bit more detail for the STM32 devices. Those have a slightly larger shim driver within Zephyr that have some abstraction that allow them to be used across multiple devices. And then finally, if we take the sort of register definitions only from the HALs, this is essentially a near-native Zephyr driver. There's not really any kind of procedural code that we're reusing, but this is just taking basically device header files that define all the register types and fields. And this is the approach that we see in the Atmel and Nordic devices in Zephyr. So a little bit about SimSys. This is something that is used across all of the ARM vendor SoCs, just about. So for those of you that aren't familiar, SimSys is an acronym for the Cortex Microcontroller System Interface Standard. It is a standard defined by ARM and has been pretty widely adopted by the different vendors. It has several different components. There's SimSys Core, which I'll get to in a sec, SVD, DSP. So the SVD is a system view description file, something used by IDEs and things like that to display, in your debugger peripheral value, or excuse me, register values while you're actually debugging. DSP is a math library targeted at Cortex-M devices, and then driver interface is ARM's kind of view of one type of abstraction. But for the purposes of Zephyr, the SimSys Core is the component that we're using. It standardizes all the processor core accesses and peripheral definitions. And so ARM provides generic Cortex-M header files, and then the vendors like NXP build device header files on top of that. And so when you put those together, you get a full description of all the registers in the SoC. Within Zephyr, the kernel port uses the SimSys register type or core accesses to talk to the NVIC and the SCB. So any parts of Zephyr that talk directly to the core registers in the C use SimSys. This is not quite true for assembly level accesses, but at least within the C realm, we see SimSys being used. And then in the driver space, we see Zephyr drivers using SimSys register accesses to talk to the peripheral registers. So about MCU Expresso SDK, for those of you familiar in the tree or with Zephyr and have been developing applications and digging into the tree, you'll see MCUX in a lot of different places. And so I wanted to cover what MCU Expresso is from an NXP view, and to make it clear what pieces of MCU Expresso are we using in Zephyr and what other things are available beyond Zephyr. So MCU Expresso is a common enablement that we do for all NXP Cortex-M microcontrollers. It's something we initially did for Kinetis devices, and then when NXP acquired Freescale, we then started to create the SDK for LPC devices as well. So this consists of peripheral register definitions that are SimSys Core compatible. And what's kind of interesting about this, I'm not sure if a lot of people know, is that the register definitions that are in SimSys are actually generated from a common database that we use to generate hardware documentation. So if you look at the reference manuals for the hardware, that comes from the same source that we use to generate these SimSys header files. Moving on to the bare metal peripheral drivers that are part of the SDK. So we built, I won't say the same, but very similar APIs across Kinetis and LPC families. And so what that means is that we have quite a few different flavors of different protocol IPs. So for example, this is a bit of an alphabet soup, but you see UART, LPUART, and LPSCI. What that means is that these are different UART IP blocks that we have on different Kinetis devices. And so what we did in the MCU Expresso SDK is to build similar APIs across these. And what that means for Zephyr is that then the next level shim is going to look pretty similar from one to the next. And so it should make it easier, once you see a UART shim, for example, moving to an LPUART or an LPSCI IP block, creating shim drivers for those should be pretty straightforward. Some of the design philosophy on building these drivers has some similarities to Zephyr in that we try to minimize interdependencies between drivers, and so you'll see an independent I2C driver, an independent clock driver, and things like that. And so one of the problems that we had in previous iterations of the SDK is that some of these had interdependencies with each other, and We tried to fix that in this current version of the SDK. It makes it a lot easier to just take one piece without getting everything if you don't need it. And then finally, the SDK also comes with a pretty large number of example projects. And the reason I bring that up here is that, you know, as we continue to build new APIs or implement APIs, you know, that haven't yet been implemented for Kinetis or LPC parts, if there isn't an example already in the Zephyr tree, there's another resource out there. And so these example projects aim to provide or demonstrate how to use these peripheral APIs. So the external folder, this is where we store all of the externally maintained source code in Zephyr. So this is not exclusively the SoC vendor HALs, but does include them. But there are other components as well, such as embed TLS, TinyCrypt, FATFS, and Sager RTT. I'm not sure if that's a complete list, but the point there is that it's not just HALs, it's also other things. So anytime we find a component out in the community that we think we can leverage in Zephyr, that's the place to put it. And that helps us to make the distinction between, you know, what is code that we've, excuse me, developed natively for Zephyr and what is code that we're using as is. So anything in the external folder, we look as, it needs to be compatibly licensed or permissively licensed, but not necessarily Apache 2. And I think most or many of them are BSD 3 clause that we have today. Like I said, we try to import code into this folder as is with minimal modification. I realize that sometimes, you know, small tweaks are needed to make the code build without errors, or, you know, rearrange things, or you know, just it's difficult to pull things as is without touching them at all. But if you do need to touch it, we like to have separate commits so the maintainers can distinguish between what was the original code, what did it look like, and what did you change to make it work in Zephyr. And lastly, anything in the external folder is exempt from the Zephyr coding style, and so that's built into the check patch scripts as well. So, you know, we wouldn't be able to enforce the Zephyr coding style on external components that we import into the project. Just recently, I think in the last week, maybe 2 weeks, the Zephyr Governing Board approved a new process to import components into the tree. So you guys are probably the first to see this outside of the core development group. So there are a couple of different things, or what the process looks like is, so if you find a component that you're interested in importing into the tree, you know, the first thing is that we need some documentation. Where did you get this code? How's it maintained? What's the license? And so that needs to be documented in a README and submitted to the TSC. And so we can leverage the existing GitHub pull request workflow to do this. So the TSC members will review the proposal, and if they approve it, they'll forward it to the governing board for review. So then the governing board, they have 2 weeks to review the proposal to import a new code component. And if nobody raises any objections in that 2-week period, the software is accepted, the README is included, and we can go ahead and merge that pull request. If a member of the governing board does raise concerns, then they have to, you know, vote on that and decide if there's alternate actions. So this is kind of the list of information that we need to document a new code component before it can be imported into Zephyr. This hasn't changed dramatically. I think there are a couple of new things that get added recently. So what's the origin? Why are we including it? What are the dependencies? What does it link to? If you get that code from a Git repository, what's the commit SHA? And then a link to the license. So That's just a quick overview of, how we're using vendor HALs, why are we using vendor HALs, and how do we get new ones into the tree. That's all I've got. Do you have any questions? Yeah. They didn't share that with us. Is Anna still here? Can you comment on that? What criteria does the governing board use? Yeah. No. No. Good question. The question was, do we pull in the entire SDK for NXP? And so the answer is no, and the reason is that we actually only distribute the SDK on a device-by-device basis. And so typically what will happen is, if somebody's interested in porting Zephyr to a new SoC, then they would go and download the SDK and import the SDK for that SoC. Sometimes what will happen is the SDK, basically we have what we call superset devices and subset devices that may have the same group of SoC, or same group of peripherals, but a smaller memory footprint, for example, and those will be part of the same SDK. And so what I've done is to try to, when I pull an SDK from the MCU Expressos website, then that's what I'll go and import into Zephyr, rather than, there's no way to get an SDK for all of the SoCs for NXP, because that's dozens, if not hundreds of them. So I try to take them as a as-needed basis, but without breaking up packages. Yes. Yes. Yes.
A lot of drivers are common between two SoCs, like SoC1 and SoC2.
Mm-hmm.
So it could be like a copy,
No.
or
No, and
that's what the HAL vendors do.
yeah,
They create the abandoned.
that's one change that I made in Zephyr when I imported the SDK is for those drivers, those SoC drivers that I know are supported in multiple SoCs, then I actually changed the directory structure a little bit. So I have within the HAL folder, I have a drivers folder, and then I also have an SoC folder. And so for the drivers that are SoC specific, that has some naming conflicts, like clocking, for example, is an example of a driver where I put that driver in the SoC folder in the HAL versus, the UART driver, which I know is supported on multiple SoCs. So I had to break it up a little bit, but wherever possible, I tried not to duplicate code.
So as a developer, if someone says that, okay, these SoCs, 5 SoCs has common UART, so driver should be one.
Mm-hmm.
So the code you have in Zephyr will differ from the code of the vendor. So
It's the same code. The directory structure is a little bit
the
different.
directory structure will change, for example. So
Yeah.
when the vendor is okay, you need approval from the vendor, or
No, I don't think there's any problem with moving things around within reason. Like I said, with the common drivers, I did make a change to the way that we release it as NXP, but I didn't change the content of the file.
the problem would arise when vendor would release another version of
Yeah, so I had an interesting suggestion recently, which I think might be a good opportunity for future work, in that, as it is today, it's kind of a manual process to do that directory restructuring. I mean, it's not significant, but I've done it a few times, so I'm familiar with it, but for somebody new to the project, it might be a little more difficult. And so the suggestion was made to just script it out, and that's probably something I'll work on in the near future.
Yeah, that would be good. In that case, there would be consistency between different SoCs so that the developer or
Yeah.
user doesn't need to. Okay.
Hmm.
And this HAL thing is a patch mode, it's gonna stay like that only. And these HAL usage, the best would be we have a driver for a different SoC, the driver directory, which is independent of the HAL. But there's too much medical tuning or things. But this HAL solution is just a patch for the time being, or it's gonna stay like that?
I think it will stay like that for quite some time. I mean, maybe as the project grows, we might see, might have enough people working on the project that we could support more native drivers. But as it is today, we don't have the bandwidth to do that right now.
And if someone wants to do it, a developer,
Yeah. If they're willing to maintain it. It's a challenge when we have so many different SoCs and so many different drivers. And we are still a pretty young project.
thank you.
Can I ask a question?
Sure.
Make a statement maybe. I'm a kernel developer, and we simply disallow HALs in the Linux kernel.
Mm-hmm.
And like we have this, it's our way or the highway. Just rewrite it like we want it in our way. And I mean, there's a reason for that. It's not like we're just generally just want things that way. And it's what you're bringing up. It's maintenance. Usually, merging a big HAL makes it gives you support for new hardware very quickly, which is nice, which you want to deliver to your users, of course. The problem is maintenance, because especially it stands in the way for internal refactoring. And somebody saying, well, you can't really change that thing in the kernel because this thing, which is a HAL and a big complex amount of code, is using it. And yeah, so keep the old ABIs around. Your optimization and so on, it's not as important as keeping this thing working. So we just simply disallowed it. So we have something called a stable ABI nonsense document. We just say like, no, don't do that. And just be aware that you might be inviting disaster here. So at least put in a policy, I would say, as when it's okay to delete HALs. Say like, this HAL is standing in the way of development, then it's okay to delete it. That's something I think would be helpful for you.
Okay, thank you. Yeah, I mean, that's not a scenario we've hit yet, but, you've certainly had a few more years.
I haven't seen that so much myself personally, but I think that would be helpful. Just like, if that is in your way, the maintainer, the company, whatever, is not willing to change it, it gets deleted.
Because like one of the problems is that like you have a developer that wants to create a native driver
Mm-hmm.
for one specific SoC, not for the entire family. But then you have the HAL that supports the entire family. So how to manage those differences, right? Like we had some conflicts with the STM32, for example, where like the suggestion was to remove the native driver and use the HAL for everyone.
Mm-hmm.
So that is kind of a little bit tricky.
Yeah, I think the trick with the native drivers is figuring out how to create a native driver that can be supported across SoCs. There's certainly, you need that visibility to know what other SoCs would that driver apply to, and that's not necessarily an easy task.
About the maintenance of the SDKs, I think it would be valuable to add in a replified patch list. Because if you want to communicate or update the SDK, you need to maintain this kind of list of what has been modified and to update it.
A patch list for what's been modified in the HAL?
Yes, if you had to make some modifications,
Well, and that's why I mentioned earlier that, I like to see, initial patch that imports the HAL and then a secondary or however many additional patches on top of that, so it's obvious what changes you had to make. There were a couple of small cases that I had to deal with, with the MC Expresso stuff. I don't know, how many changes you had to make to STMQ, for example. But at least using Git as a method to do that, then you can naturally look at the Git history.
Doing the exercise regularly to update package. Easier when you have a separate file that says, okay, this file is being modified, take care of it.
Yep. Anything else?
Do we always kind of force like a maintainer when importing a HAL from, because like we know that you're working behind, like NXP,
Right.
you have people working behind other companies.
Right. No, I mean, the Atmel HAL, for example, I mean, we don't have somebody from Atmel working on it. There has been a guy that's kind of been taking that role outside of Atmel. But we don't have a whole lot of cases of that yet. But it's a good question.
Because like bringing like back to one of like when we decide to remove something,
Mm-hmm.
it's always going to be kind of a conflict. And if we have, of course, like an active maintainer from a company, it's easier. It's better, and you trust it kind of more than if somebody else just imports somebody else's code in there.
Mm-hmm.
It's important to have a maintainer.
We need more maintainers. All right. Well, thank you.